Okay, ladies and gentlemen, let's make sure some things are enabled here. All right, well, good morning. I hope you guys are doing well. Let's see, I did upload the software this morning, so there's been a few items that need to be worked on. So let's kind of fix a few things since we're here. Anyway. Let's fix a few stuff. This is kind of annoying to me. Yeah, anyway, okay. Calculus lecture went pretty good despite the upload of the software and things, but okay. Well, let's kind of regroup and remember what's going on here for us, right? So I hope you guys are well. Good morning to you. And I'm going to go to our browser here and hopefully get to see our browser. There we are. Okay, go to, ladies and gentlemen, your class. I'll go to your class. Okay, here we go. 227 and online transition. I just want to remark that I have put up some examples for you guys here for the binomial. I might have mentioned this to you guys yesterday, right? So I put up those examples. I highly recommend you go over these because these are some of the questions that were in the notes. So I really highly recommend you guys review this. And here's a good example too, right? 12 question multiple choice test. So go over these. Make sure you guys can do this work because, you know, figuring this out at the last second the night before is not how you study. By then it's too late. So I have this work for you guys uploaded. I went through this like I promised you guys. And some of these are questions that we actually didn't go over. But I put these examples online for you guys to review. Okay. Anyway, there you guys go. And as you guys know, we started on the Poisson probability distribution here. And like I said, there was a typo I found in the, in the worksheet there. And I fixed it and I uploaded this. So anyway, here's what you want to do. So let me do a couple of things here, right? I'm going to try to go and let's see how well this works. Let's go to the iPad. And, all right, this is the first problem we did on that worksheet. Okay. If we recall, let me see here. We could do a couple of things. Math 227, Poisson. All right, so I'm going to show you here. Here's some of them that we did. And in fact, I think I like going into Word a bit better. This is the last class, sorry. So let's see if we can find this. Let's go to 227. We need Poisson. There we go. Okay. So this is what we were working with. And if you guys remember from yesterday, X was the number of arrivals in an interval. That's going to be important. Mu is the average number of arrivals. Remember what we said about this. This here, ladies and gentlemen, this value is your past. This is known, right? This is from the past. And that's the average. That's what mu is. And let's put a note here. Different books. I don't even like that color. Maybe this is better. Different books describe that average. Mu, you can see it as lambda. So they replace, instead of mu, you got a lambda in your Poisson probability formula. So I want to make sure that that is, again, the average. That's the mean, the expectation. That's what you're using in your formula. So yesterday we started where, no students visit. Remember we said in this case that meant X is 0. 1 student visits, X is 1. X is 2. X is 3. X is 4. That's the student visitors. And again, since I repeat myself, some books use lambda. And the reason I say that is because the TI used lambda, right? It didn't use mu. But it doesn't matter. It's the mean. It's what's expected. So we're looking at yesterday the number of arrivals in an office hour. This is the interval they're talking about, right? So we talked about this yesterday. We have 4 on average, lambda or mu, right? 4 students, I'm going to stick to that, arrive in a 60-minute interval because that's an office hour. And then they're saying in a random office hour, what's the probability? So we're all set to go. So let's use our formula here. We did this one yesterday. Check. We had from yesterday P is 0. Right? Let's write this down. And that was approximate. P is 0. We found to be 0. Here, it's over here. Right? 0.0183. And that's to the nearest 10 thousandths. Okay, so we're going to continue with this. And notice, I did follow this procedure yesterday. And like I said, this is lambda. That's lambda in the TI world. So we're going to find the rest. We have to find P of 1, P of 2, P of 3, P of 4. All right, so question 2. 1 student arrives. And I think I said visits, but it doesn't matter. They're arrivals, they're visitors, they show up, right? X here is 1 because X is the number. Remember how we do this? Of student arrivals, visitors. 4 is the average or typical number of arrivals. So the formula really looks like this. P of X is, if I write it down, remember, how you remember a formula is every time you use it, you write it down. P of X is mu to the X, e to the minus mu, over X factorial. And this is kind of some of the things I wanted to talk about. But anyway. So plug everything in. Right, we know X is 1, so here's an X. Here's a 1. Mu here is 4, so there's a 4 there. So we'll say here P of 1 becomes 4 to the first power, e to the minus 4 over 1 factorial. Now, just doing a little bit of, algebra. 4 to the 1 is 4. That's 4 e to the minus 4 over 1 factorial. So some of you guys may not know, but let's define for you what factorial is. I want you guys to note. Factorial. There's a definition of that. So factorial, if you see in your calc, you really have something called and factorial, and that's going to be and followed by symbolically an exclamation point. That's really known as and factorial. The definition is if you guys can count backwards, you're finding out what factorials are. Okay, so you start with n. Here's where you start. And you end with 1. And you simply count backwards. So you have n minus 1, n minus 2, n minus 3, all the way down to 3, 2, 1. You're counting backwards. That's really the definition of a factorial. And you might say, okay, what is 3 factorial? Well, start with 3 and count backwards. 2, 1. You start with 3, you end with 1 always. So if you know what 3 times 2 times 1 is, which is 6, you just found 3 factorial, by the way. Okay, here's an example of that. 4 factorial. Start with 4 and count backwards. You start with 4, and then 3, and then 2, and you always end at 1. And so if you know what 4 times 3 times 2 times 1 is, you might say this is a little bit more difficult. Okay, 4 times 3 is 12, times 2 times 1. 12 times 2 is 24 times 1. Guess what 4 factorial is actually going to be? 24. And then similarly, you might say, hey, what's 5 factorial? We'll start with 5, 4, 3, 2, 1. Harder to compute. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So ladies and gentlemen, 5 factorial is 120. And so on. So, I mean, these are the values here, and I'm going to give you guys some facts because you might say to me, or let's give you another example before we do that. How about 2 factorial? Right? 2 times 1. Start at 2, end at 1. That's 2. So we've seen some examples of factorial. However, here's a problem. Here's a couple of facts. 1 factorial, you can say, do I start at 1 and end at 1? Yes. So let's not actually box that yet. 1 factorial is actually 1. That's kind of maybe a little bit obvious. Maybe not. Sorry. But let me give you something that's not so obvious. 0 factorial. Well, 0 factorial, ladies and gentlemen, is also 1. So 0 factorial is 1. 1 factorial is 1. That doesn't follow from the definition. This is not obvious. However, let me show you something via the TI. So I have to find my TI. There's TI. Let me prove this to you because we can put 0, go to math, all the way down to PRB. If you want to go to the factorial keys, go down to 4. There's a factorial. It's math, probability, factorial. And we say, okay, we want 0 factorial. Hit enter, and sure enough, it's 1. Right? You want to try it for 1. Math. Scroll to PRB. Down to factorial. Hit enter. This is also 1. So what I'm showing you guys here is even though it really doesn't follow from the definition, if you guys want to know the truth, this stuff doesn't follow by definition because of how we define things, right? Okay. Well, let me remark about this here for you. The real definition goes beyond the scope of the course. This is what the definition becomes for some nice counting numbers, or I should say whole numbers, because whole numbers are 0, 1, 2, 3, and so on. So this is what this is for whole numbers, but there is another function that is really at play here, and it goes beyond the scope of the course. But anyway, you guys can learn how to do this. I should say, you could just use this definition with a couple of facts that 0 factorial is 1 and 1 factorial is 1. And then altogether, you might say, well, how do I use that? Well, you have it here. 1 factorial is what? You don't want to do that. 1 factorial is 1. So that P of 1 is 4 e to the minus 4. This is going to give us the probability that we'll have one student arrival, one student visitor. Okay? So, I mean, this I'm going to have to use, obviously. I'm going to go to ITI. And here now, I'm going to put down 4 times second e to the minus 4 power here. And this is going to give me my answer. And this is going to be to the nearest, let's do it still 10 thousandths. So you can approximate this to the 10 thousandths position. So let's go to the iPad here. All right, you guys okay with that one? So let me move some of these things here for us. Okay. Just moving things around on my end here. And the iPad is actually like this, so. What's going on here? Yeah. I guess it wants to be in the middle. Okay, here's the probability of one student arriving, and that's going to be 0.7326. One student arrival. Now, you might say to me, can I use the TI and take advantage of the built-in functions there? Right? Some of you guys might want to use built-in functions. You say, I go to distributions, that's blue. Second, it's that VAR, it's distribution key. Go down to the Poisson. And it's going to be past, it's going to be C. Poisson PDF. It's also in my notes. Hit enter. Notice the mean is still 4, but the X value is now 1. Hit enter. And we get 0.7326. We get the same answer. So you guys can use either of these. And then I'm looking at this here. Boy, what's going on with these overlays? Weird. Yeah, updated the software and got some weirdness here. Anyway. All right. There you guys go. So you can use the calculator this way as well. It's up to you. So here's how we handle the Poisson. And some of you guys, hopefully you guys were here yesterday for that. But let's go to the next question. And you say, well, what's the next question? Well, now they want to know, question 3. We have 2 students arrive. Well, in this case, X is 2. P of X is mu to the X, e to the minus mu over X factorial. You plug in a 2 wherever there's an X. Mu here is still 4, so I'm going to plug that in 4. All right. So P of 2 is 4 squared e to the minus 4 over 2 factorial. So what I choose to do whenever I work with this, okay, whenever I work with the Poisson, probability formula, I do my arithmetic. 4 squared I know is 16. 2 factorial, we know, is 2. So P of 2 is 8 e to the minus 4 because we take 16 divided by 2. Now, what that means for us, for those of us who are using calculators in a different way, if we go to the TI here, right? All I do is take 8, multiply it to e to the minus 4. And here's what we end up with. Rounded to the 10,000ths is 0.1465. Okay, and let's move that there. Okay, this is to the nearest 10,000ths position. And so this is how we work with this. And if we want to verify by using the distribution function, I see second distribution, it's in blue. You're going down to Poisson PDF C. 4 is still there. Change this 1 to 2. Paste this. Sure enough, it's the exact same answer. So ladies and gentlemen, this is the chance that we have 2 students visit in an office hour when the average number is 4. This is working with the Poisson probability formula. Question 4. 3 students visit or arrive, right? So that means x is 3, right? Mu is still 4. P of x, mu to the x, e to the minus mu. Over x factorial. So you're going to plug in these values. You're going to plug in here 3 for x, and you plug in 4 for mu. P of 3, 4 cubed, e to the minus 4 over 3 factorial. I know 3 factorial is 6, and I know 4 cubed is 64. Okay, 4 times 4 is 16, times 4 is 64. Never hurts to do some arithmetic. P of 3 is 64, e to the minus 4 over 6. So we can actually deduce the chance we have 3 students arriving here. So if I go to my TI now, and we say, okay, TI, let's clear this out. I can take 64 times e to the minus 4 power. Let's get out of that position. Let's get out of the power position. Move that out. And then we have to have divide by 6. We're going to get 0.1954 if we approximate this to the nearest 10,000ths. And we're trying to get a nice square here. Okay, so let's double check here. Since we're on this calculator page, let's see what the distribution menu brings us. And let's go down to this C Poisson PDF. The value of x now here is 3. We get the same thing. Good. All right. There we go. So ladies and gentlemen, this is a good exercise here in how to use our calculator, our formula. This is the Poisson probability distribution. This is arrivals, right? So if I go to the last question on that list, 5, and we say 4 students arrive. I believe that's the last one. Yeah, 4 students arrive. We actually say 4 students visit. Doesn't matter. X counts the number of arrivals in an interval. So in this case, X is 4. Mu here, ladies and gentlemen, is also 4. So they're really asking us, hey, what's the chance that 4 people arrive, 4 students arrive? When on average, 4 students arrive. P of X is mu to the X, e to the minus mu over X factorial. All right, let's go back. I'm sorry about this. We got to go back to the iPad. You guys can't see any of this. Here's what I've been writing down. So you guys could take a look at what we've been writing down. This is the last question on that, or the 5th question on the worksheet, going through how to use this. Okay, 4 students visit, 4 students arrive. X is 4. Right? Plug in a 4 wherever there's an X. Plug in a 4 wherever there's a mu. P of 4 is 4 to the X, e to the minus 4. 4 to the 4. 4 factorial. So let's really double check. Yeah, it looks like this is what we have here. Now, if we go to the TI, and I say to you, okay, let's go to that TI calculator. Can I even enter all of this in the TI? Yes. Let me show you. I'm going to do this. I'm going to make this a little bit more sophisticated here, right? I'm going to put 4 raised to the 4th power here. 4 caret 4. Come out of the power position and say times e second, right? It's in blue, e to the minus 4 power. Come out of your power position and put a parentheses. So here's my numerator. Don't forget, I need to divide by 4. Oops, let's put another parentheses, because I have work to do on the bottom in the denominator. I'm going to take 4. Now I need factorial. Math, I go all the way to probability, scroll down to exclamation. There we go. And then close this. So ladies and gentlemen, here is what you see really in the iPad. This is what you guys see right here. Here's my numerator. And here's the denominator. Don't forget, we are dividing here. So that's all in the TI. And let's see what we get. The answer is to the nearest, what is that again? 10 thousandths. What this is saying, 0.1954. All right, here we go, ladies and gentlemen. Let's see if the distribution function in the TI gives us the same exact answer. Go back. Here's Poisson. Enter. We have to have the value 4 here. And sure enough, it does. So, ladies and gentlemen, this is how we start to answer Poisson probability questions. And this is actually what you guys will need to do, in using your calculators. So the chance that 4 students visit is about 0.1954. That's about a 19.5% chance. That's the same as P of 3, by the way. Okay. And we can think of these things as arrivals. Now, here's going to be a twist. Of course, if I said to you, all right, ladies and gentlemen, let's focus on the idea. Let's note. Let's do a couple of things here. The questions I like to ask you guys are the following. If you guys know, let me go back to let's go back to the notes here. Right? We answered these 5 questions and I show you how to do it in our notes. And then I even say to you guys, I have some additional questions. These are my favorite. Right? What's question 6? At least what? 2 students visit. At least 2? I'm sorry, at least 1. That's x is greater than or equal to 1. Question 7 is at least 2 students visit. Well, that's x is greater than or equal to 2. Question 3 is more than 3. X is greater than 3. Question 4. No more than 4. That means x is less than or equal to 4. Question 5, between 2 and 5. 2 is less than or equal to x, which is less than or equal to 5. So these are all of my favorite kinds of questions, as you guys already know. Right? These are the ones you really need to study and work for. They have to work on. They have to do with language. They have to do with process. This is why you're here. All right, this is the deal. So if we look at this question for at least 1 now, like question 6, at least 1. At least 1 student arrives. You do this exactly the same way you did with the binomial and the regular arbitrary distribution. So x is greater than or equal to 1 by definition, right? That's 1 or 2 or 3, and then that goes on forever. This is not a fixed number of trials. So I'm going to put these dots big. This is not a fixed number. Remember, for the binomial distribution, that was a fixed number. Since we're counting arrivals, if you guys remember, x is the number of student arrivals, right? In theory, x can go on forever. Well, not really, because you only have a finite number of students, but you guys get the idea, right? This is the very, very, very famous concept of going to infinity. Right? When you go on forever, that means just continue.
To infinity and beyond.
What was that?
To infinity and beyond.
That's what we're talking about. So if we're going to have to add all these probabilities, we would die before we can finish this. I know. That's a lot of numbers to add. But as you guys know, what have we been saying here? This portion is by the definition. There's really 2 ways we can answer these questions. One is by the definition, and then one is by using our, you guessed it, complement rule. Okay? You could use the complement rule yet again. So I hope you guys studied those things because they're back. Complement rule is here to stay. P of 0. Do you guys remember what P of 0 was? P of 0, go all the way back to P of 0. Oh my God, that was yesterday. P of 0, we found that. That was the first question we did. Oh, 0.0183. This was P of 0. So I take 1 minus that number, 0.0183. And I'm going to plug it right here. So this is going to give me my answer. So I don't have to actually go to what again?
To infinity and beyond.
I don't have to go that far. So the TI is going to say to us 1 minus 0.0183. And we get 0.9817. Okay, so it's 0.9817. So we go back to the iPad, and I'm going to say to you guys, take a look. This is the probability that at least one student will arrive. And this is how you guys want to answer these kind of questions here. Okay, this is what you guys are doing here. And you guys know at least 2 students arrive. At least 2. What does that look like? X greater than or equal to 2. Just like before. So the probability that X is greater than or equal to 2, P of 2 plus P of 3 plus P of 4. And in theory, these 3 dots mean, what do they mean?
To infinity and beyond.
They mean to keep going forever. We'll die before we can actually add an infinite number of values. So remember, this is by what? Definition. What do you want to use? I'm going to write it in red. The complement rule. But let's remember what that does, right? What does that really do? I need to know, since by definition at least 2 is 2 or 3 or 4 or 5 or forever, I would need to know which outcomes are not here. I subtract those. Well, P of 0 is not here, and P of 1 is not here. So if I know P of 0, and I do, 0.0183, and if I know P of 1, well, we have that one too. P of 1 way back here, this is the first one we did today, is 0.7326. It's in our notes, 0.7326. Here's what you end up with. 1 minus 0.0183 minus 0.0326. So we end up with now, if we compute this, let's go to the TI. 1 minus 0.0183 minus 0.7236. We end up with 0.2581. So it's about 25, almost 26% chance that at least 2 students will show up in a typical office hour. So I want to make sure you guys understand here how we really go about finding these answers here, okay? So this is the language we care about, right? This is what I've always said to you from the very first day. Language and process is what you do. Oh, did I make a mistake here? Oh, thank you. Thank you, Cindy. My dyslexia this morning here. Let's find out. I believe Cindy is right. I think I just caught it as well. You guys know why? Yes, 0.7326. So if we go back to the TI, good. Here's the mistake. So it's supposed to be 1 minus 0.0183 minus not 0.7236, 0.7326. Yes. Okay. And we get 2491 there. Good. So let's change that here. Thank you, Cindy. Good. We get, let's get blue here. Where's blue? 0.7491. All right. That's still about a 25% chance. It's a 25% chance that at least 2 students will visit in an office hour. Pretty good. Pretty good. Now, this is actually question 7. So if we go to question 8 now. Question 8, in case anybody forgot, question 8 is going to be, I have it here, more than 3 students. X is greater than 3. So we have to know, thank you, Cindy, we get rid of that. We have to know greater than 3. What does greater than 3 actually mean again, right? Greater than 3 means more than 3. P of 4 plus P of 5 plus P of 6. Of course, you guys know by now, this means to go what? How far do we keep adding?
To infinity and beyond.
Yes, we'll die before we add an infinite amount of numbers. So this is by definition. Use now the what? Complement rule. 1 minus. Now you have to tell me which outcomes are not here. Right? P of 0 minus P of 1 minus P of 2 minus P of 3. This is by the complement rule. So, by the complement rule, we have to know what all these numbers are. And let me go and try to write it over here so everybody's aware, right? We need to know P of 0. We have that one. P of 0, we could go back up here. 0183. P of 1 is 0.7326. We need P of 2. And, P of 2 is right up here. Oh, we didn't use it. P of 2, I guess we have to go all the way back to P of 2. 1465. Check your notes. And then we need P of 3. So P of 3 is all the way back here, 0.1954. So we're going to have to do some computation in that TI. So TI, okay, let's ask you to do this for us. 1 minus 0.0183 minus 0.7326 minus 0.1465 minus 0.1954. So I'm going to ask you guys to double check to make sure I actually put the right things. Okay, hopefully I did. And I did it. Excuse me. There's a mistake here. Anybody know how I know there's a mistake? Probabilities are never negative. Let's double check here. 1 minus 0.0183, that's P of 0, minus 0.7326 minus 0.1465 minus 0.1954. And this is disturbing again. So let's double check to make sure everything's okay. More than 3 students arrive. Okay, that means 4, 5, 6. So I subtract 1 minus 0, 1, 2, and 3. So let's check these values. Let's check P as 0. .0183 for P of 0. 0.7326 for P of 1. And is that okay? 0.7326. Something's bothering me about that one. Let me check here again. Let me do this here. 4 times second e to the minus 4. Oh, there's a 0 there. Yeah, there it is. Oh, my God. Oh, my God here. Okay. Oh, there's a 0. There it is. The first problem of the day was a problem. You guys have to double check and help me out here. I'm such an old man. You guys have to help me. Anyway, that's P of 1. Is P of 2 okay? What's P of 2? 8 times second e to the minus 4 here. Yeah, okay, so it looks like P of 1 has to change. So what that means here for us is this is going to be different too. Right? This is 0.0733. And then this is going to change our answer. So let's do 7 again. 1 minus 0.0183 minus 0.0733. So we get 0.9084. Anyway, this is what you guys would do on a test because, like I said, at 0.733, the second you get a confusing answer means you did something wrong. Okay, so let me go back to the iPad. Here's what I'm saying. P of 1 for question 7 is 0.0733. So that's going to change our answer for question 7 for at least 2 students because that's a different P of 1 value. So we corrected it. This is the right answer. And then we go to question 8 and you go, okay, I needed P of 1 right here. Well, there it is. This is the corrected version. Okay, so now when I answer question 8, let's go to the TI with the corrected values. 1 minus 0.0183 minus 0.0733 minus 0.1465 minus 0.1954. Double check again to see if I'm okay. All right, I need you guys to help me out here because, you know, what happens is, well, who knows? .5665. So, ladies and gentlemen, this is the probability that more than 3 students will arrive here. Okay, more than 3 student arrivals. All right. That's pretty good. Let me get something here. All right. Really weird. All right, whatever. Question 9. Let's see what question 9 is. Question 9, they want to know no more than 4 students. So no more than 4, as you guys know, no more than 4 is short for not more than 4. It can equal 4. It just can't be more, so it's less than or equal. So the probability that x is less than or equal to 4 is p of 0 plus p of 1 plus p of 2 plus p of 3 plus p of 4. Now, notice something here. This is by definition, and I'm going to do it this way here. Let me go back. This is by definition. If you use the complement rule here, it's 1 minus the probability of the outcomes that are not here. So that would be p of 5. That would be p of 6. That would be a whole lot of outcomes. That would be, again,
to infinity and beyond.
You would die before you finish subtracting if we use the complement rule. So I'm going to say to you guys, in this case, you use the definition. We're adding p of 0 all the way up to p of 4. So I have to have those values, right? So luckily, I do. P of 0, some of these values are here. 0.0183, right? Here's p of 0. P of 1, P of 2, P of 3. So I'm going to take these values, 0.0733, and the next one is 0.1465. And the next one is 0.1954. Then I have to find P of 4. P of 4 is, let's see, where are you, P of 4? Go back. It's again 1954. That was right. Okay. So we get to add these numbers here, right? P of 0, P of 1, P of 2, P of 3, P of 4. So it's going to be in our TI calculator. And TI, we say, let's clear this stuff. It's distracting. Take 0.0183 plus 0.0733 plus 0.1465 plus 0.1954 plus 0.1954. Enter these values. And hopefully we didn't make a mistake, but I want you guys to double check. Double check that we didn't make a mistake. 0.6289. And that's about like 63%. So 63% of the time, no more than 4 students arrive. And this is how we go about these here. All right. Now, I'm going to say to you guys here, I want you to finish number 10. 6289. Thank you, Joanna. That's right. We got the same answer. Good for you guys. Now, I'm going to have you guys finish number 10 between 2 and 5 students because I want to go back and talk about this thing about the interval. So Let's talk about this interval idea. If I go back to Word and I say, okay, Word, if you can. Oh, all right. Here we go. Notice what we're talking about now, right? They're saying now in this question, here's a transition, ladies and gentlemen. What they're saying to us now is in the next, what's this? 38 minutes of an office hour. In the next 38 minutes of the office hour, what's the probability that no more than 2 students will arrive? Now you say, no more than 2. I know what that means. That's x is less than or equal to 2. No more than 2. I know what that is. Okay. No more than 2. X is less than or equal to 2. Good. But the problem here now is you just changed the interval. They're saying in the next 38 minutes, that's not 60 minutes. That's not an office hour. So this is where the issue is. That's not 60 minutes. We need to do something here. Here's what I'm saying. What is the new mu? You say new mu? Yeah. It's not 4. So you see, we have 4 student visitors in 60 minutes. 4, let's write this down. 4 student visitors every 60 minutes. We know that. We're writing this down. Well, if you think about this, this is really a proportion. You see, 4 students will visit in 60 minutes. Some unknown student visitors in 38 minutes. So, this is going to be the visitors, and this is time. This is the visitors, and this is time. Okay? 4 students visit in 60 minutes. That's the same as an X number of visitors in 38 minutes. So what I'm going to say to you guys now is, here's the question. What is X? Well, this here is what we call a proportion, equal ratios. Use algebra. Whoever said algebra wasn't useful? AB 705. Oh my God, whatever. Anyway, here we go. Let's do some arithmetic here, right? We're going to multiply both sides by 38. So we get the following here, okay? And this is part of the reason I gave you that homework in that first lecture. We get 38 times 4 divided by 60 is that value of X. Now, I got news for you guys. It's not really an X value. So I'm going to get rid of the variable X. It's really our new mu. So mu here in the 38-minute interval is going to be 38 times 4 over 60. I have to do some arithmetic. I have to change that. 4 times 38 divided by 60 gives you a mu value of 2.533. Let's do another one, 3. Okay, that's again to the nearest 10 thousandths here. So this is the mu I have to use for question 11, 12, and 13. Okay, I have to use this different mu value. For question 14 and 15, they changed the interval to 72 minutes. It's done the same way. But anyway, let's do the following. Let's finish question number 11, no more than 2. So for question 11, and we're going to remind everybody, this is in a 38-minute interval, right? Mu, you have about 2.5333 students visit. This is the average. Students will visit in the interval of 38 minutes. So your Poisson probability formula looks like this. It's still mu to the x, e to the minus mu over x factorial. But if we use the mu to be 2.5333, 2.5333, here's what your formula becomes. P of x is 2.5333 to the x, e to the minus 2.5333, everything over x factorial. So your formula changes, ladies and gentlemen. You have a new mu because this is in 38 minutes of an office hour as opposed to the full 60. So if you said, all right, Mr. Judge, this question, which is, I guess it was 11. Yeah, number 11 here. Wasn't that number 11 no more than 2? And yes, the interval is different. No more than 2 is x is less than r equal to 2. 0, 1, and what? 2, ladies and gentlemen. 0, 1, and 2. So what this means is, and let me write down our mu. We're going to have to use the Poisson probability formula for the values of x being 0, 1, and 2. And then we add these values. Well, let's use the TI. So what we've been seeing, how we've been using this stuff, is we've been going through, let's do the distribution here, right? Let's go to the distribution and find Poisson. It is C. This is a different mu. I know they call it lambda. Same thing like we talked about earlier. 2.5, 3, 3, 3. And then we want an x value. We want 0 here, okay? And in fact, let's go again to the nearest 10 thousandths. 0.0794. So make sure we have those zeros there. Let's do this again, okay? We're going to find now when x here is 1. So distribution. Change your x value. Oops. X now is 1. Is that right? And we get, for this value, 0.2011. All right. We're on our way. This is P of 1. We now need P of 2. Distribution in blue. Scroll to Poisson. Hit enter, and now we have the x value to be 2. And what do we get? 0.254. That 6 next to the 7 makes it an 8. Okay. Double check the iPad here. Double check. Let's see if these answers are what we just found. P of 0 is right here. 0.0794. P of 1 is 0.2011. Okay. And P of 2, 0.2548. Here we go. Now, all we got to do, ladies and gentlemen, as you guys can see, is add these values. So 0.0794 plus 0.2011 plus 0.2548. And ladies and gentlemen, here's what we end up with. 0.5353. And that gives you, the chance that no more than 2 students will visit in an office hour when you are now in a 38-minute interval. So let's make sure we know that here. This isn't a 38-minute interval. So, this is how we go about these things. How about question number 12, which will say less than 4 students visit. You have to know what less than 4 means. Less than 4 means strictly smaller than 4. Well, 0, 1, 2, and 3. All these outcomes are smaller than 4. Okay, and so if you're really awake here, you have a lot of these values already. That's 094. This is 2011. This is 2548. Okay, we just need P of 3. Okay, we have all the other values. We don't have P of 3. But with a TI, we can get P of 3. We can say distribution Poisson. Change this to 3. And we get approximately 2.5 or 0.2151. Now, some of you guys are going to say, hey, Mr. Judge, couldn't I have taken my last answer and since I already add P of 0, P of 1, P of 2, can I add the P of 3 to the last answer? And if you're awake, sure. So I'm going to say to you guys, take the last answer, which is 0.5353, and add that to 0.2151. And we get a final answer here of, this is equal to 0.7504. Which is a 75% chance, okay? So, ladies and gentlemen, just to go through this here for you guys, this is a 75% chance that less than 4 students will visit, okay? And that's, again, in the 38-minute interval. Okay, pretty good. Pretty good. So let's look at the next question here, right? Number 13 here. See if we can sneak that in. I think we could sneak it in. 13 is at least 3 students. And again, at least 3 is x is less than or equal to 3, because that means 3 or more. So the probability, at least 3, apologize, it's been already a long morning. Right, at least 3 is that x is greater than or equal to 3. Right, 3 or more. That's at least 3. So we have P of 3 plus P of 4. And as you guys know, with the 3 dots, that means add these things forever.
To infinity and beyond.
And then again, that's by definition, right? And what you know here is you have to subtract P of 0, P of 1, and P of 2, because you would die before you can add an infinite amount of numbers. All right, so use the complement rule. So this answer, 1 minus P of 0 minus P of 1. We have a lot of these values. P of 0, P of 1, P of 2. P of 0 we know is 0.0794. P of 1, 0.2011. P of 2, 0.2548. So all I did, ladies and gentlemen, was go back to the prior question and notated these numbers here, P of 0, P of 1, P of 2, because I'm going to take these numbers, I'm subtracting here now, okay? So we're going to get this answer here. Going to the TI. 1 minus 0.0794 minus 0.2011 minus 0.2548. Let's double check. See if we get this correct here. That's 0.4647. And let's double check here, okay? 0.4647. Now, let's see. I think Cassandra has a question here. Let's see, Cassandra, what do we do here? With the definition, you add, and with the complement, you subtract, right? Absolutely. Yes. Cassandra, your observations are correct. But let's be how should I say, specific. With the definition, yes, you're going to be adding probabilities with every single definition. And that is the pattern you guys have noticed. And you say, what do you mean, right? Well, what does this mean? At least 3, right? At least 3 up here. The definition of at least 3 is you have 3, 4, 5, 6 forever. That's at least 3. That's 3 or more. And so, yeah, by definition, you're adding. The problem is you're adding what? Forever.
To infinity and beyond.
You'll die before you can finish. So by the complement rule, if you guys remember that, this is, yes, by definition, you're adding. But by the complement rule, it is always 1 minus. 1 minus what? It's 1 minus the probabilities that are not in the definition. So you say, what's not in the definition? 0 is not there. 1 is not there. 2 is not there. You're subtracting all of those. Don't go to 3 because 3 is in the definition. So Cassandra's observation is, with the definition you're adding, with the complement you're subtracting. Yeah, exactly. But be careful. You're subtracting the outcomes that are not in the definition. That's your complement rule. Subtract the outcomes that are not in the definition. And so, yes, we certainly end up with 0.4647 with this final answer. Now, I'm going to do the following. I'm going to upload again for you guys in this worksheet. If you go back, this worksheet, we did not do question 10, 14, and 15. So there's about 3 of them we didn't do today. And so what I'll do is I'll upload to my website the examples, okay? In the example portion, these questions we didn't get to today. So you guys have all the information here. Now, I did give you guys some book work. I'm looking this up. Did I give you book work on Poisson? Or I always say what? Poisson. Right? Double check to see the book work I gave you guys. I might still have it. No, I don't think I did. Maybe I didn't give you book work. Well, we have web work, of course. And for that, we got to go to the browser. And you got to go to 227. We got to go to, not that one. That was the old site. The new site. So take a look at statistics lecture 11. So the homework on the web. Statistics lecture 11. Of course, you guys do. I usually say do them all because you have, answers to half of them. And on the book, right? So let's get to the book. We have section 5.3. This is on Poisson. And I'm going to say to you guys, you're going to do 5 to 15 odd here. Now, it's a very good setting to work with probability distributions. And in fact, it's all around us. Last night, there was an earthquake in LA. Did you guys feel that earthquake? Did it wake you guys up? I know, I got woken up by it, but there was an earthquake in LA, right, last night. And close to Inglewood, I guess. So we can think of even earthquakes as arriving. And so as I was up and I'm looking up earthquakes and blah, 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 I guess I read about an earthquake somewhere else happening. And then they said, oh, but there's a 1% chance in the next week, at least one earthquake above this value will occur. Listen to all that language. This is the Poisson probability distribution for you, ladies and gentlemen, because we can think of earthquakes as arriving, earthquakes as showing up. And we can count them if they're above a particular value, like 5 or 4 or 3, whatever. So last night, yes, we did have an earthquake, and I'm going to use this information. There is a chance, ladies and gentlemen, there is a chance, this is the Poisson in action, that in the next week, that's the interval, there's a 10% chance there'll be an earthquake that's even larger. Now, I'm not going to use the word a earthquake. I'm going to use at least one earthquake because it could be 2 or 3 or 4 or 5. So there's a 1% chance in the next week, at least one earthquake larger than what you had last night will occur. This is the Poisson probability distribution in action. You guys can see some examples like that in your book. And that's why I love the book questions. And I worked on the web stuff, and you got the book stuff. You got all of it together. So ladies and gentlemen, this is one of my favorite distributions because it has to do with real life. And yes, hopefully not. I know, Jackie, you felt that. Cindy, I know how you're feeling. But you guys want to know something? This stuff is real. It is out there. And you guys are educated on this. You can now talk to people about this, okay? But an earthquake arriving is a Poisson distribution. And you say, well, how do they know the average number? Past history, they gather the data. So they gather data on earthquakes. So this is how, with that mu or lambda, this is how we can use this stuff to predict the present or the future. So enjoy your Poisson distribution homework today. Work on this stuff because, as you guys know, it's the real deal. All right. So if you have any questions, come to my office hours. They're going to begin in about 5 minutes. If you have trouble getting in, email me and I'll let you in the door. All the usual things. So stay safe. Have a good evening and take care. Work on your homework.